Okay, class, and today we are going to finish up chapter 2, and we're going to finish the last section, section 7, and we're going to talk about graphing techniques. And we're going to talk about stretching and shrinking graphs, reflecting graphs, symmetry of a graph, which is also going to lead us into even and odd functions, and translations. Okay, so what's going to be neat about this is all going to be starting with the basic functions that we went over last time. So a lot of this things that we're going to talk about all uh, can be graphed by if we understand how the basic functions look. Okay, so if we look at each one of these functions, okay, so g of x equal to 2 times the absolute value of x. Okay, we can compare the values by the basic function. Okay, so we can compare these two the values for both of these functions. And we're going to see that for corresponding x values, the y values of g are going to be double those of f. Okay, so basically we're taking g of x, you could say is twice f of x, right? Because f of x is defined as the absolute value of x, right? So we could look at it that way as well. Okay, and so if we fill out our table for corresponding x values, we see that same pattern going on. And so this is what it would look like. So here's our basic function, right, that we talked about before. And then notice what's happening. It makes the graph more narrower, right? It's going up at a steeper rate, or it's going up faster on both sides, right? What about if we take h of x equal to 1/2 of that value? Well, then, as you probably might think, it's going to now cause it to go down by 1/2. So we're going to see the same general shape of that of f of x, but in this case, it's going to be 1/2 of f of x, which causes a shrink, right? So in the last one, it was a stretch, it was a vertical stretch. And so in this case here, it's going to be 1/2. So h of x is 1/2 of our basic function, f of x. Okay, and so this is what we have. So this is our basic function, and now it's shrunk, like, or sometimes it's called compressed down in the vertical direction. Here it shrinks in the vertical direction, right? So it goes down. Okay, where in the other one it was stretched up in the vertical direction. Now, let's take k of x. Now, look what happened here. Now we're bringing the 2 inside the function, right? So now we're taking x and we're multiplying x by 2. Okay, so now we're going to use the property 2 of the absolute value. So we're going to use this property that we talked about in the review, and we're going to say AB equals the absolute value of A times, there should be times, the absolute value of B. And so we can rewrite this as the absolute value of 2 times the absolute value of x, so we get 2x. So what happens is we get 2 k of x is equal to this. Okay, so the graph of k of x is the same as the graph of g of x that we saw before in part A. Okay, so what happens? Well, this brings up the idea of vertical stretching or shrinking of a graph of a function. Okay, so it says suppose that A is positive, and if a point lies on the graph of f of x, then the point x, A times y, lies on the graph of A times f of x. Okay, because we're multiplying y values. So this is f of x, so y equals A times f of x. Okay, so here, if A is greater than 1, then the graph of y equals A times f of x is a vertical stretch. So if it's greater than 1, so if this A value is greater than 1, it's going to be a vertical stretching. Okay, if A is between 0 and positive 1, okay, then it's going to be a vertical shrinking. Okay, so if it's less than 1 but positive, it's going to be a vertical shrinking. If a is greater than 1, then it's a vertical stretch. Okay, now what if we now taking inside the function, and so we're going to say, hey, now we're going to multiply x inside the function by a, and so a is positive, some positive a. Okay, so before we were outside the function, now we're going to be inside the function. Well, now we're manipulating x, right? We're doing something to x. Okay, so if a is between 0 and 1, it's going to be a horizontal stretch. Okay, so if a is between 0 and 1, it will be a horizontal stretch. Excuse me. If a is greater than 1, then we're going to have a horizontal shrinking. Okay, so again, gotta remember what's going on. Are we doing something to x? So are we inside the function? So are we multiplying by a inside the function, or are we multiplying by a outside the function? And then we have to look at the intervals from 0 to 1 and 1 to infinity. Okay, so we're greater than 1. Okay. Now reflecting. So what we're going to do is reflecting, we form a mirror image of a graph across the line called reflecting the graph across the line. Okay, so this is when we reflect across the line, it could be the x-axis, it could be the y-axis, it could be some other line. But what we're doing is we're forming the mirror image of the graph across that line. And so if we want to do this, so here we have negative square root of x. So we know what the basic function, square root function looks like, right? But now what we're going to do is we're going to take all of those values and we're going to take the opposite of them. So what are we doing? We're taking all the y values and we're going to take the opposite of them. So what are we doing? We're reflecting the square root function across the x-axis because we're taking all the positive values of y and making them negative. Any negative values of y, we're making them positive. Okay? And so that's what we're doing. Okay, so we're taking this f of x, right? And we're taking all of the values of f of x and we're making them the opposite value. Okay? So here's f of x, and so what we're doing is we're making them positive. The ones that are positive, negative, and any that are negative are positive. Okay? And so what happens is we're reflecting the graph across the x-axis. So whenever we're multiplying by -1 outside the function, like in this case, it's a reflection about the x-axis. Now, what if the negative sign is inside the function? Well, then this becomes a reflection about what? Well, all the x values are now going to flip signs. So all the positive values of x are becoming negative. All the negative values are becoming positive. So this becomes a reflection across the y-axis. Okay? And you see, in this case here, when x is -4, it's undefined. But when it's taking the opposite value, it becomes 2. So here, 4 was 2, and -4 is undefined, but now here, -4 is 2, and 4 is undefined. So it flips across the y-axis. And this is what it looks like. So here's our graph, and it flips across the y-axis and becomes this one. Okay. Now, reflecting across an axis, here's the general rule, just like I was saying. Y equals negative f of x is the same as the graph of y of x reflected across the x-axis. Okay, so we're taking the y of f of x, reflecting across the x-axis to get this one. Okay, if a point x comma y lies on the graph of y of f of x, then x comma negative y lies on this reflection. Okay, the graph of y equals f of negative x is the same as y of f of x reflected across the y-axis. So if the negative sign is inside the function, it's a reflection across the y-axis. If the negative sign is outside the function, it's a reflection across the x-axis. Again, we're looking at the basic functions, right? First, we're looking at the behavior of the basic functions, and then the negative sign is going to tell us how it's reflected. Now, symmetry with respect to an axis is, hey, how can if we can fold it across an axis where the left and right or up and down or both sides of the axis are the same. Okay, so a graph of an equation is symmetric with respect to the y-axis if replacement of x with the opposite of x gives you the exact same function. Okay, so if you take f of x and you replace x with negative x and you simplify it algebraically and you get the exact same function back, it's symmetric with respect to the y-axis. Okay, the graph of an equation is symmetric with respect to the x-axis if the replacement of y with negative y gives you the equivalent expression. So if you take the y values and replace y with negative y, and then you simplify it, and you get the exact same equation or function back, then it's symmetric with respect to the x-axis. Okay. So now what we're going to do is let's test for symmetry with respect to the x-axis and the y-axis. So with the x-axis, what are we going to do? We're going to replace x with the opposite value of x. Okay, so we're going to first do that. And so now we start with this, and now we're going to replace x with the opposite value of x. Remember, don't forget the parentheses here. So because we're squaring x. So if we're going to replace x, we have to square the whole thing. And so what do we get? Well, negative x times negative x gives us the same thing, positive x. So we get x squared plus 4, and we get the same thing. So this is symmetric about the y-axis. Okay, so it has y-axis symmetry. Okay, so the result is the same as the original equation, so the graph is symmetric with respect to the y-axis, just like we did. Now, what if we substitute negative y for y? This does not result in an equivalent equation. We can see that from the graph, right? We can see that this is not going to be symmetric with respect to the x-axis. But again, it's good practice to show. So if we basically replace this with negative y, and then we basically multiply both sides by negative 1, we get y equals the opposite of x squared minus 4, which is definitely not the same thing that we got, or that we started with, rather. Okay, so it is not symmetric with respect to the x-axis. Okay, now what about this one? Okay, well, first thing we're going to do is, if we want to look at the symmetry, let's replace y with negative y. Okay, well, if we replace y with negative y, well, look what happens. We get the same sort of thing going on. Okay, again, we are squaring the whole thing, and we get equivalent expressions. So now, since we replaced y with negative y, and we get the same expression, we know that this is going to be symmetric across with respect to the x-axis. And of course, we can see that it is a sideways parabola like we talked about before. Okay? Okay, so now we can see that the graph is symmetric with respect to the x-axis, but is not symmetric with respect to the y-axis, as you can see from the graph. And again, if you plug in negative x here, you're not going to get the same expression. Okay? Now, what about this one? Well, now, if you can see something here, if you remember from our discussion of circles, this is an equation of a circle that's where? Centered at the origin. And so this is definitely going to be symmetric across the x and y axes, but let's prove it, right? So we're going to replace each one of these with negative x and then with negative y, and we'll show that we get the exact same thing. So if you replace this with negative x, you're going to get x squared back out, and so you get the same thing. And if you replace negative y or y with negative y here, you're going to get y squared again. So in both cases, you end up with the original equation back. And so this is going to be symmetric with respect to both axes, which you would expect from a circle centered at the origin. Okay, and there it is. Okay. Okay, so now we're going to test this one. Okay, let's use here, in this equation here, we're going to replace x with negative x. Okay, and if we replace x with negative x, well, we're going to get negative 2x plus y equals 4. Okay, so that doesn't work. If we replace y with negative y, we get negative y is equal, negative y, and we get 2x minus y is equal to 4, which still does not give us the original equation. So in this case, this is not symmetric with respect to either the x or y axes. Okay, so it's possible that it's neither going to be symmetric with respect to x, nor is it going to be symmetric with respect to y. Okay, and according to the graph, you can easily see that this has no symmetry with respect to x or y. Okay. Now, what about symmetry with respect to the origin? What does that mean? Well, the graph of an equation we call symmetric with respect to the origin if we replace both x with negative x and y with negative y, and we get the same results as the equivalent. So if we replace both of them at the same time, right, and then we simplify it, if we simplify our expression and we get the same function that we started out back, then it's symmetric with respect to the origin. Okay, so for example, going back to our circle, we can replace x and y with negative x and negative y, and we're going to get the exact same thing back out, right? And so not only is the circle symmetric with respect to the x and y axis, but now we can say that it's symmetric with respect to the origin. What does that mean? Well, what that means is we can actually rotate the graph 180 degrees and we'll get the exact same graph back. Okay. Now what about this one? So y equals x cubed. Okay. And so if we replace this with negative y and we replace this with negative x, what are we going to get? Okay, so let's do it. So we get negative y and we get negative x cubed. Well, what happens here? Well, negative x times negative x times negative x will give us a negative quantity x cubed, right? So we're going to get this. And then we divide both sides by negative 1 and we get the same equation. So yes, this is symmetric with respect to the x-axis. Okay. Now, again, keep in mind, what does it mean to be symmetric with respect to the origin? It means that if you look at the graph and you can rotate it 180 degrees, right, on its point, right, on its inflection point or on its I can't think of the term, but its point of rotation, then if you can rotate it on that point of rotation for 180 degrees and you get the exact same graph back, it is symmetric with respect to the origin. Okay. Another way to look at it is if you put in the opposite value of x and you simplify this and you get the opposite of y, that is also another technique. But let's stick with this one here. It's 6 half a dozen others. So here they're replacing both x and y with negative x and negative y respectively. And if you get the exact same function back, it is symmetric with respect to the origin. Okay. So a graph is symmetric with respect to x and y axes is automatically symmetric with respect to the origin. So we saw that with the circle, right? So if we can show that it's symmetric to both the x-axis and the y-axis, then it has to be symmetric with respect to the origin. A graph symmetric with respect to the origin need not be symmetric with respect to either axis. Okay? So it doesn't go the other way around. Okay? A graph symmetric with respect to the origin need not be symmetric with respect to either the x-axis or the y-axis. Of the three types of symmetry with respect to the x-axis, y-axis, and origin, a graph passing any two types must also exhibit the third type of symmetry. So in other words, if it is symmetric with respect to two of the three, then it has to be symmetric to all three. Okay? A graph symmetric with respect to the x-axis does not represent a function. Okay, so remember that. Why? Because if it's symmetric with respect to the x-axis, okay, then that means it's going to be something that does not pass the vertical line test. Okay, so here's the summary table. So here we go, symmetric with respect to x-axis. You're going to replace y with negative y, and you get the exact same function out. For example, this is an ellipse that is symmetric with respect to the x-axis, right? And it's definitely not symmetric with respect to the y. Okay. Here, to be symmetric with the y-axis, you replace x with the opposite of x, and if you get the same equation back out, then you're going to have that y-axis symmetry with respect to the x-axis. For example, this parabola. And then here, if it's respect to the origin, you replace both x and y with the opposite values of x and the opposite value of y respectively. If you get the exact same graph or exact same function back, it is symmetric with respect to the origin. And for example, look at this one. This would be a cubic function. And notice that if you do rotate this 180 degrees, you get the exact same value back. If you rotate this one across the y-axis, you get the same value back. You get the same graph back. Likewise, if you rotate this one about the x-axis, you get the same graph back. Now, even odd functions. Now, a function is even if you replace f of x with f of opposite value of x, negative x, and you get the same value. In other words, if it's symmetric with respect to the y-axis, it's an even function. Okay. If you plug in the negative value of x and you get the opposite of f of x, then it's odd function. Okay. So if you replace x with the opposite value of x and you get f of x back out, it's an even function. So all graphs that are symmetric with respect to the y-axis are even. And if you take a function and replace x with f of x and you get the opposite value of f of x, then it's an odd function. Okay? And this type of graph is symmetric with respect to the origin. So odd functions are symmetric with respect to the origin. Even functions are symmetric with respect to the y-axis. So now let's decide whether this function is even, odd, or neither. Okay? So right away I can see that this is going to be an even function. Okay? And I'll show you in a minute. But let's prove it. Okay? So we're going to replace x with the opposite value of x and see what we get. So we get f of negative x is equal to this and this. And so what happens? Well, because these are even, these are going to end up being positive x's again. And so you're going to get the exact same value out. And so f of negative x gives you f of x. And so this is an even function. Okay? So notice that all of the exponents on the variables are even. If that's the case, this will always happen, and you're going to end up with an even function. But again, this is a shortcut. Be aware that I may ask you to prove it or show algebraically. Okay, so but again, you could see immediately that this is going to be an even function just by the fact that all of the exponents are even. Okay. Now what about this one? Well, right now I'm going to tell you that this is going to be an odd function. Okay, but let's prove it. So we're going to replace all the x's with opposite value of x, negative x. So we get negative x quantity cubed, and then we have negative x here. And notice that this is going to give us a negative value, and this is also going to be a negative value. So this is going to become a negative, positive. This is going to become a negative. Now if we pull out the negative sign, we get the opposite value of 6. We get the negative of the quantity 6x cubed minus 9x, which turns out to be the opposite value of f of x. And so this is an odd function. But also notice that all of the exponents on the variable are odd. So if all of the exponents on the variable are odd, you have an odd function. If all of the exponents on the function for the variable is even, then you have an even function. Okay? But again, make sure you are able to prove it algebraically. Now, notice that here we have an even exponent and an odd exponent. Well, this is going to be neither. Okay? But let's prove it algebraically. So we're going to replace all the x's with negative x. Okay? Again, don't forget parentheses where they're needed. So this is squared, so this is going to become a positive x again. But this is an odd function. This is an odd exponent, so this is going to become negative, and it's going to become an opposite. So now you get 3x squared minus 5x, which is definitely not the same thing that we started with. And even if we were to factor out a negative 1, we're not going to get the original. So this is going to be neither even nor odd. Okay. Now, what about this one? So here we have the absolute value of x minus 4. Okay. Well, what does this mean? So we know the basic function, so now we're going to talk about translating functions. So let's say g of x is the absolute value of x. We know what that basic function looks like. But now we're going to subtract 4 from it. So we're taking our basic function and we're subtracting 4. Okay. So again, let's take our basic function f of x equal to the absolute value of x. And then we're going to say g of x is our function here that we want to compare it to. So what's going on here? Well, when x is negative 4, f is 4. But g of x is 0. When x is negative 1, f of x is 1. And what? G of x is negative 4. Or, excuse me, negative 3. Okay? And then when 0, we get negative 4. When 1, we get 1 and negative 3. Okay? So what's going on here? If we look at this, it looks like our value of g of x is 4 less than our original value of our basic function, f of x. And so what do we get? We get a vertical translation. It moves the whole thing down 4 units. So every point of f of x is being translated down 4 units. And notice that we're subtracting outside the function. So we're affecting all the y values, right? So all the y values are going down by 4. So now, if we're given a function g, and it's defined as f of some other function, f of x plus c, then what we're doing is we're adding to every single y value of f of x. So this is going to be a vertical translation up. Okay? So we're going up. We're moving up c units. Okay? So if it's addition, it's a vertical translation up. If it's subtraction, we're going a vertical translation down. Okay? But notice that we're outside the function. Now in this case here, we're bringing it inside the function. So now we're subtracting not from y, but we're subtracting from every value of x. So what happens? when we're subtracting, this is going to be a horizontal translation. In fact, this is going to be a translation to the right. Okay? And to see this again, draw your table. So here are all the x values and the corresponding y values. Here's f of x. This is what we get for the absolute value of x. And now we're going to compare that to the absolute value of x minus 4. Okay, so here we go. We're going to look at this. So in this case here, when x is negative 2, f of x is 2, but here, g of x is 6. Okay? So when x is 0, f of x is 0, and g of x is 4. So what's happening here? Well, think about this. When x is negative 2, f of x is 2. Well, when is g of x equal to 2? When x is 6. So these values, in order for g of x and f of x to be the same, what's going on? It's moving what? It's moving over, right here, 2. Okay, so it moved over 4 units. Okay, and so when you're inside the function, when you subtract inside the function, it's going to have an effect on the basic function that you're moving and translating it to the right that many number of units. Okay, so here's the original basic function, absolute value of x. And so what's happening here? Well, when x is 0, the basic function is 0. Well, the translated function is 0 when it's moved 4 units, so at x equals 4. Okay, so when x is 4, you get 0. And so that's why you get this horizontal translation to the right. Now, if you add, guess what? It's going to be a horizontal translation to the left. Okay, so if you have a given function g, and it's defined by some other function, right, x minus c, it's going to be where c again is a real number. For every point on the graph of f, there will be a corresponding point at x plus c, comma y. So it's going to be a translation to the right. Okay, if it's x plus c, then it's going to be a horizontal translation to the left. Okay, and let's see here. And this one says the graph of g will be the same as the graph of f, but translated c units to the right if c is positive, or c units to the left if c is negative. And this is what we call a horizontal translation. So if you're adding or subtracting outside the function, then you're looking at a vertical translation. If you're adding or subtracting inside the function, then you're looking at a horizontal translation. Okay, so here we have the original function, and so this would be plus 2, right? So you're translating it to the left 2 units, and here is negative 3 or minus 3, so it's going to be a translation to the right 3 units. Now you got to be careful here. So errors occur when horizontal shifts are involved. Okay, to determine the direction and magnitude of a horizontal shift, find the value that causes the expression x minus h to equal 0. This is the best place to do that. So find when it's 0. Okay, for example, if you have this, you want to find when this is 0. Okay, so while this is 0, when x is 5. So this is translated 5 units to the right of y equals x squared, because this is a squared function. So this is going to behave like x squared, but since we're subtracting inside the squared function, right? We're inside the function. This is a horizontal translation. And if we look at x equal to 5, when x is equal to 5, this is 0. As opposed when x squared is equal to 0. So this is equal to 0 when x is 0. This is equal to 0 when x is 5. So guess what? It's moved, translated horizontally to the right 5 units. Okay, now what about this one? Here, we have x plus 5. Well, how are we going to make this 0? Well, again, it's the same basic function, right? We know this is 0 when x is equal to 0. When is this going to be equal to 0? When x is equal to negative 5. Well, that means we moved it to the left, right? So that means this thing is a translation to the left 5 units. So that's another way to test which way is it going, by finding where the function is equal to 0, okay, when it comes to these types of translations, okay? Now, what about graphing this function? So we know this is going to have what basic function? What basic look is it going to be? It's an absolute value function, right? Well, what are we doing to the absolute value function? We're doing 3 things to it. We're taking the absolute value of x, and what are we doing? We're adding 3 inside the function. So this is going to be a horizontal translation to the left. And then we're adding 1 outside the function. So this means we're going to be translating it up 1 unit. And then what are we doing? Well, we have this negative sign out here, so this is also going to be a reflection about which axis? It's going to be a reflection about the x-axis. Okay, so the first thing I would do is deal with the reflection first. So we can reflect the basic function, absolute value of x, and then after we reflect it, then we can do the translations. Okay, so to graph this function, the lowest point on the graph of y equals absolute value of x is translated 3 units to the left and 1 unit up. The graph opens down because of the negative sign in front of the absolute value sign expression, right? So making the lowest point the highest point on the graph now, okay? Because it's reflected about the x-axis. And so the graph is symmetric with respect to the line x equals negative 3, okay? And so this is what we get. Okay, so what they did was they took this point here. This is the main point that was here. Okay, and they translated it up, or excuse me, they translated it, up 1 unit, and then they translated it to the left 3 units. Okay, instead of opening upward, because of the negative sign, it opens downward. Now what about this one? Now again, it's an absolute value function, but what are we doing? This time, we're multiplying x by 2, okay? So we're inside the function, and we're multiplying x by 2, so this is going to be a horizontal stretch, right? And then we're basically subtracting 4 from x, right? And so it's going to be a translation to the right, right? So this would have to be 2 to be 0, okay? So this is going to be 2 things going on. Okay, we're going to factor out of 2. Okay, so if we factor out of 2, so this is another way of doing it. Okay, we can factor out of 2 from using the techniques or using the properties of absolute value signs, because we'll get 2 times the quantity x minus 2, all in absolute value signs, and then we can use that property and rewrite it as the absolute value of 2 times the absolute value of x minus 2. Okay? And so this just becomes 2, and we get 2 times the absolute value of x minus 2. Well, we know this is going to be 0 at x equals 2. So this is a vertical translation, right? Right? Or horizontal, yeah, horizontal translation to the what? It's going to be to the right, 2 units. And so it's a vertical translation to the right 2 units, and then it's also a vertical what? A vertical stretch as well. Okay, so again, if we left it like this would be a horizontal stretch, and then after the horizontal stretch, we're subtracting 4, and then again, we're taking the absolute value. So either way, we'll get the same way. Either whether you factor out the 2, which is fine, and use the properties, you're going to get the same graph. Okay, now what about this one? So this is a square function, right? So the basic function is a squared function. But what are we doing to the squared function? So there's our f of x. What are we doing to it? We're taking 1/2 outside the function. So this is a vertical compression or vertical, what do they call it? Shrinking. So a vertical shrinking. It's also a reflection about the x-axis, and we're moving the entire graph up 4 units. So g of x is going to have the same basic shape as x squared, but it's going to be wider because it's being shrunken vertically, and it's going to be reflected about the x-axis because of the coefficient is negative, and then it's going to be translated up 4 units. Okay, so we have a parabola that started here and opened upward, right? And so what happens? It gets moved up 2 units, or if it's upwards, we're going to take half, right? So it's stretched out. So if we plot this, we get 0, 1, and 0, -1, right? So we get -1, 1 here, and we get 1, 1 here. And if we use the 1/2 here, then it becomes what? 1, 1/2, -1, 1/2. And then it's negative, which means it gets reflected down here, right? Well, then what we're going to do is we're going to add 4, so we're going to translate it up to here. So again, understanding the basic functions, understanding how the basic functions work and how they're graphed can help you graph a lot of these other graph squared functions, absolute value functions, whatever the functions may be. Okay, so now here's what we have here. Okay, so we have a graph of a function defined by f of x. So it's a weird looking graph, right? A lot of things going on. And y of x is shown here. So it says use the graph to sketch each of the following graphs. Or use this graph to sketch each of the following graphs. So here's our basic graph. So, so this is what we're going to start with. So this is how we're defining f of x. So now what we're going to do is we're going to take g of x is f of x plus 3. So what does this mean? We're going to take f of x and we're going to move it up 3 units. So this point is going to go to here. This point is going to go up here. This point is going to go up here, and so on, right? So all these points are moving up 3 units. Okay? And so we get something like this. Now we have f of x, f of the quantity x plus 3. So now we're adding 3 inside the function. So what's going to happen to this function? F of x is going to be what? Translated to the left 3 units. So it's going to have the same function, but now it's going to be translated, all the points are being translated to the left 3 units. Okay, now what about this one? So now we've got two things going on, right? So now it's going to be moved up 3 units, like the first one, and then it's going to be moved to the right 2 units. So every point on the graph of f of x is going to move up 3 and to the right 2. And so we'll end up with something like this. Now what about this one? Well, here we have the opposite of f of x, which means this is a reflection about the x-axis. So we're going to take f of x and reflect it across the x-axis, so we'll get this. Okay, so notice that this point, and this point stay where they're at, and this point was here, and this gets reflected to here. This point was here, and this got, here, and this got reflected to here, right? So all of the points got reflected across the x-axis. So here is the summary of the techniques of graphing functions based on our basic function. So understand those basic functions. That's going to be the key to make this really easy. Okay, so in the descriptions that follow, assume that a is greater than 0, h is greater than 0, and k are greater than 0. And in comparison with some graph, y equals f of x. Then, if we add or subtract outside the function, we're translating either k units up or k units down, respectively. If we add or subtract inside the function, that's going to be a translation left or right, respectively. If we multiply by a outside the function, that's going to be a vertical stretch, right? So it's going to be a vertical stretch, okay? If a is greater than 1, and it's going to be a vertical shrinking or a vertical compression if a is between 0 and 1. If we're going to multiply a by f of x, or excuse me, multiply f of x by a, is a horizontal stretching of the graph f of y if a is between 0 and 1, and a horizontal shrinking if a is greater than 1. Okay, notice that here they switch the two conditions, right? Okay. Oh, hold on a second. This is, this a should be inside. That's not right. Yep, sorry, this is typo. This a should be inside. It should be ax. Okay, so, oops. Let's see here. Yeah, so this should be ax in here, not out here. And then, of course, the last thing is our reflections. If our negative, it's outside f of x, it's a reflection across the x-axis. If it's inside, it's a reflection about the y-axis. Okay, so that is the end, not only of this section, section 7, but also of this chapter. Okay, so please, this is a big chapter. Make sure you take the time to practice and familiarize yourself with the summary, okay? And practice doing translations, practice reflections, practice doing the combinations of reflections, stretches, shrinking, things like that, okay? Because if you and make sure you understand the behavior of the basic functions, the absolute value functions, squared functions, cubic functions, square root functions, cube root functions, and so on. Okay, make sure you understand that, because that's going to be the starting point for doing all of these types of sketching or translations and reflections and stretching and shrinking. Okay, Until then, again, practice with the suggested homework. Bring your questions to class. Be ready to work, and make sure you watch these videos before the day we cover them in class. Okay? Take care. Have a great day, and I'll talk to you later.